Okay, before we go on to the other two methods of charging, I do want to show you two quick things that are both simulations on the computer. So we're going to go and look at the computer. Okay, so this is actually something you can do at home. I couldn't find either a glass rod or a rubber rod for this, but this is something that you can do at home to show polarization. So all this is an aluminum can, just like a soda bottle. And let's see here, if we click show charges, so we can see that there are a whole bunch of negative charges that are spread out here. And what you'll see is once I put the other objects in there, they're also positive charges under those. Watch what happens when I put in a rubber rod. Okay, so that rubber rod you can see is negatively charged. Look what happens. Because there's negative charges now, the electrons, the negative charges, tend to move away. That exposes some positive charges up here. So we've got more negative charges down here, more positive charges up here. That means the positive charges are attracted to this rod. The negative charges are repelled away from it. Watch what happens if I move the rod around. The negative charges will move to repel away from it, but the positive charges that are closer to it, the rubber rod, attract, and I can actually make the aluminum can move back and forth. And this is something you can actually do at home. Okay, if I take the rubber rod away, oh, there we go, and I put a glass rod on instead, the opposite happens. The glass rod is positively charged. The electrons are attracted to it, so they go towards the glass rod, and that makes the negative side of that aluminum can attracted to our glass rod, so it will move towards it. You can do all sorts of things on this, and I'll show you the link for the website if you want. Even if I put both of them on there, then I get some neat effects. But this is polarization. There's no touching of the rod and the can necessary. No charges are being transferred. They're simply moving around, and that's causing the can to move towards or away from the rod. That's causing one side to be more attracted than the other, so it rolls towards that side. Kind of interesting. The other thing I want to show you is, I believe, yes, it's this one. Okay. So I just wanted to show you a quick example of creating a charge through friction. Let me do this. Okay, see that? Watch this. We rub the balloon on the sweater. The balloon becomes negatively charged. What that means is that the sweater must be positively charged, if that is in fact the case. Okay, so I just wanted to show you those two real quick. We're going to go back to the notes for a little bit. Don't worry, we'll see more simulations in a little bit. We're going to talk about our second method of charging, and that would be charging by conduction. Okay, so you've talked about conduction before, maybe not in a charging sense, but definitely in a scientific sense before. When you talked about methods of heat transfer, back in maybe earth science or middle school science, conduction was heat transfer through two objects directly touching. So conduction in a charging sense means you take a charged conductor, something that's already charged, and you touch it to another charged or uncharged conductor. What will happen is electrons will travel from the object that is, as I like to say, more negative, the more negative conductor, to the less negative conductor. So what this essentially means is the one with the most electrons. Now you might say, well, what if one of them is positive? Or what if both objects are positive? Okay, you can't really say one's more negative than the other. In that case, it would mean the one that's least positive. The one that has the most negative charge or the least positive charge will send electrons to the other object. The more negative conductor to the less negative conductor. Okay, if the two conductors are identical, as in same size and everything, this flow of electrons, by the way, flow of electrons, what does that mean? A flow of electrons you know as current. A current, a flow of electrons, will happen until the objects have the same charge. So let me draw you some pictures of how this works. Example, a metal sphere with an excess of 8 electrons comes in contact with a metal sphere with an excess of 4 electrons. What will happen? So let's draw our two spheres. Here's the one with 8 extra electrons. I'm just going to write this one is more negative because it has more negative charges. It has more electrons for its net charge. And then we also have this identical one that's identical except it is less negative. Okay, so more negative always means trending towards having closer to, let's say, an infinite number of electrons, the biggest possible negative charge. Now, what happens if we touch them together? Well, conduction says that as we touch them together, electrons will flow from the more negative to the less negative conductor. How much will they flow? Will all of them go over there? Well, no. We'll have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. But let's say 2 of them are going to start to kind of make that bridge the gap. Electrons move in order to balance the charges on each object. If we then separate them once this has occurred, we'll end up with 2 objects with the same charge. They will have equal charges by the end. That is how conduction works. You take 2 objects with different charges, you touch them together, they have to be conductors. Electrons will flow from the more negative object to the less negative object until the charges are equal. So, let me show you another example. A metal sphere with a charge of positive 3 times 10 to the negative 6 coulombs comes into contact with a metal sphere with a charge of negative 5 times 10 to the negative 6 coulombs. What will happen? So, this time we don't have we can't draw in all those charges. That would take forever. We're not going to do that. Instead, what we're going to do is we're just going to label each object with its charge. This is positive 3 times 10 to the negative 6 coulombs. This, since it's positive, has a lack of electrons. We also have this identical, except for charge, object, negative 5 times 10 to the negative 6 coulombs. This has an excess of electrons. Now, what's going to happen when we touch them together? Well, what will happen is the electrons go toward the less negative, or in this case, you could think of it as, I don't know why I put a slash there, less negative or more positive conductor. In other words, they'll flow this way, okay? There's too many electrons over here. Remember, electrons don't want to be near other electrons, so they will move over to this conductor, okay? They'll go where there is a seeming lack of electrons so that they can spread out more. Now, what happens at the end? What's the charge on each at the end? Well, we're not quite sure. There's some rules in order to figure this out. If you were just given charges like this and not just like a couple electrons on each, here are the rules. Add the total charge up, including the sign. So if it's negative charge, you have to include that negative sign when you're adding. Split evenly amongst objects. What happens here is just like up before, when we have equal charges at the end, the charge will be split evenly. So essentially what we're doing is we're adding up these charges, and we're dividing by how many objects we have. It's almost like finding an average, okay? So when we add this up, 3 times 10 to the negative 6 plus negative 5 times 10 to the negative 6 equals, we put that into scientific notation. Let's see here, let's write this, 3 times 10 to the negative 6c plus a negative 5 times 10 to the negative 6c. that equals, let's see, 1, 2, 3, 4, 5, 6, negative 2 times 10 to the negative 6 C. That's the total charge in this problem. Overall, we have more negative charge than positive charge, so the net charge of both objects combined is negative. We're going to divide that in half, and we end up with negative 1 times 10 to the negative 6 C. So that's the charge that ends up on both objects. We took a positive object and a negative object, and due to them sharing charge between them, we end up with two objects that are actually negatively charged because there was a net amount of negative charge in the problem before they touched. And once again, we see that there are equal charges. So the idea with conduction is that the charges at the end will always try to equal out. Okay, they'll always try to equalize so that we have the same charge on both objects. Again, I'm going to try and show you an example of this. It might take a little bit of work, but here we go. I'm going to show you again on the computer. So let's go back to that example we had before with the balloon and the two metal objects. What I'm going to do is move the metal objects down here so that they are touching. And look what happens now. I've got this object polarized so that one side is positive, one side is negative. This is polarization, right? Now, what happens if I separate these two objects? Well, now I have a positively charged object and a negatively charged object. I'm going to remove the balloon. And then, what do you think is going to happen if I make these two objects touch each other? What should happen is this has way too many electrons. This is the more negative one. This is the less negative one. It has way too many electrons. They want to spread out. They're going, if they touch, the electrons are going to go from this object to this object. There we go. And for some reason, it doesn't quite always perfectly work out. Have to do that for some reason. But what should happen is they should equal out in terms of their charge. Okay? Now, I'm going to do this one more time. Get my balloon. Touch the objects together. Okay. And then I'll explain this in a later video, but what I'm going to... nope, I didn't want to do that. What I'm going to do is separate this, and now I'm going to remove the balloon, and I'm also going to get some more negatives up there. Okay. So now what I have is I have an object that one object has a charge of -8, the other extra electrons. The other object has a charge of +2, so two more positives than negatives. If I were to touch these together, what would the charge on each of them end up being? Well, what I would do is I would add up the total charges. -8 plus 2 should be -6. And I need to divide that by 2 because there's two objects here. If I put these two objects together, what should happen is ultimately they should both have a charge of -3 at the end, meaning 5 electrons went from the -8 object to the +2 object and gave them both a charge of -3. Let's see if that actually happens. Almost. Like I said, sometimes this doesn't quite work out perfect for some reason. I think it's just oh, that really didn't work out. This is what I get for trying to do things. Okay. Anyways, you see that both of them worked out so that, and this isn't, you know, the best. This is a pretty good simulation, but sometimes it's got a couple of glitches. You see that the charges equal out, okay? Electrons will always try to move so that they are as spread out as possible, and that's what charging by conduction takes advantage of. We're trying to spread out the electrons so that they're as spread out as possible, and what will usually happen in this case is that you touch two objects together with different charges. Electrons will move from more negative to less negative so that both objects at the end will have the same charge. We're going to come back with one more video on charging by induction, but until then, I will let you be. All right.